This is going to be the final lecture on the X-ray diffraction part of this course. And in this lecture, I want to take another look at the international tables for crystallography. We had quite an elaborate look at these tables, and one final look from the point of view of diffraction. Let us consider the space group P2 sub 1. Now, this space group, what we have done here if you recall, in a primitive monoclinic lattice, one has added two-fold screw axis. So, two-fold screw axes are at the corners, are at the centers of the edges and in the center of the cell, and this is how the motifs get rotated around by the screw axis, or the general positions get rotated around by the screw axis at all the four corners of the cell. And now we just directly come to what are the general positions in this. So, the general positions are essentially, if I put an atom at the coordinates, at general coordinates x, y, z, a second atom would be generated at minus x, y plus half, minus z. So, it is rotated by 180 degrees and then translated parallel to the screw axis by half, and the screw axis is along the z axis. So, you get along the y axis in this case, not z axis. So, there are two atoms per unit cell in this. Now, I want to now look at this specific thing, reflection conditions that are given along with this general position. Essentially, this is saying that a reflection from 0 k 0 will only occur when k is an even number, k is equal to 2n. Now, how does one get this? So, if I put an atom at a general position, the screw axis rotates and produces a second atom. So, I have essentially two atoms. Now, suppose I put a second atom at another general position, then that will also get replicated and produce two more atoms and so on. So, in general, I can put, let us say, n by 2 atoms at n by 2 different general positions. And the screw axis will then generate another n by 2 atoms by the action of the symmetry element 2 sub 1. So, therefore, I will have a, this will give me a total of n atoms, then all of them need not be the same. In fact, n by half of these atoms could not be same or may be same, depending on what kind of a structure we are dealing with. So, if I have to write the structure factor for this, so the structure factor F, I will sum over n by 2 atoms only. Fj is the jth scattering factor for the jth atom, and I put it at some general position x, y, z. So, e to power I 2 pi h xj plus k yj plus l zj, and a second atom, because of the screw action, will give me a second term in this for the jth atom I 2 pi I have minus x, y plus half, minus z. So, minus h xj k times yj plus half minus l times zj. So, this is how the structure factor would look like. Now, what I do is, let us specifically look at the HKL plane 0 k 0. If I look at this, my structure factor becomes j is equal to 1 to n by 2. Fj, the first term would become xj and zj are put 0. So, I have e to power I 2 pi k yj plus the second term will give me e to power I 2 pi k yj plus half. Now, this could be written in the following way. I can take e to power I 2 pi k yj common, out here this will be fj, and what I am left with is from the first term 1 and from the second term it will be e to power I pi k, because k yj is common, has been taken out. So, I am left with e I 2 pi k half. So, 2 and 2 will get cancelled and what I am left with is e to power I pi k. Now, this value would be plus 1 for k being 2n, it will be minus 1 when k is equal to an odd number 2n plus 1. I already used n here, so let me use this as m is any integer. So, therefore, f is equal to 0 when k equals 2m plus 1 and not is equal to 0, which means reflection will occur when k is equal to 2m. So, this is from where this reflection condition is coming. So, even though it is a primitive lattice, because there is a screw axis, we are going to get some extinctions. And in fact, to generalize this, any time when there is a symmetry element which has a translation. So, the screw axis is one of them, the other one is glide plane, that also has a translation built into it, you are generally going to get some extinctions. Whenever you have a centering translation, like in a end centered crystal or a face centered crystal, again there are going to be centering translations and therefore, you are going to get some extinctions. Now, this was a fairly simple case, and one must also note here that there are no special positions here. Otherwise, when there are special positions present, then we have to test out the special positions also by putting atoms on the special position and then checking what kind of reflection conditions one gets from those as well. So, coming to the space group number 5, C2, this is essentially an end centered monoclinic crystal, unique axis is B along with the two-fold symmetry axis is there, and one has a centering translation, the C face. So, this is the A axis, this is the C axis, this is the vertically up would be the B axis, this essentially is your C face over which there will be a lattice point at the center as well. So, there is a centering translation of half A plus half B. So, let us look at the Wyckoff positions for this. So, when I put an atom on a general position at x, y, z, the centering translation would produce another atom at minus x, y, minus z. Here I have just magnified the Wyckoff positions and I have also added to the right the reflection conditions. So, let us examine what happens here. So, I think I made a small mistake, I will just repeat this. When I put an atom at general position x, y, z, minus x, y, minus z is the second atom produced as a result of the two-fold rotation axis. And then we add the centering translation here half 0 to get the position for the other two atoms. So, when I put one atom, I will get 4 atoms and therefore, the multiplicity of this general position is 4. So, here you can see this clearly x, y, z due to rotation minus x, y, minus z, add 0, 0, 0 and add half 0 to both of these positions and one will get a total of 4 So, what I will get in addition to x y z and minus x y minus z, I will also get x plus half, y plus half, z, and one will get minus x written as bar x plus half, y plus half, and z bar. Let us try to analyze this. So, I will have now 4 terms in the structure factor, and of course, if I put n in this case n by 4 atoms, I will get total of n atoms, and each of those could be different. But we do not need to really write along with the summation, because we just have to add one atom at a general position. So, I will get 4 atoms. So, just write 4 terms of the structure factor, that is good enough to analyze the reflection conditions. So, starting with x, y, z, second one I get minus x, y, minus z. Third position I will get adding half of 0 to each of these, x plus half, y plus half, z, minus x plus half, y plus half, minus z. So, the structure factor F can be written as, and I am writing only for one kind of atom. So, I can just write the scattering factor as simply F and write down the 4 terms. So, e to power I 2 pi hx plus ky plus Lz, second term e to power I 2 pi minus hx plus ky minus Lz. For the third atom, e to power I 2 pi h x plus half plus k y plus half plus Lz. Final term e to power I 2 pi h of minus x plus half k of y plus half minus Lz. So, I have these 4 terms in this, which can be written as in the following way: 1 plus e to power I pi h plus k, and I will have 2 more terms here. So, that will give me total of 4 terms again, e to power I 2 pi hx plus ky plus Lz plus e to power I 2 pi minus hx plus ky minus Lz. You can confirm this, that on expansion I will get the all the 4 terms written above. This again, this would be plus 1 h plus k even minus 1 h plus k odd. So, this will give me a reflection condition, because f is not 0, and this will give me extinction. So, we are looking at the space group C2, and if I just go back, basically these reflection conditions are saying the same thing. If I look at this one here, HKL, H plus K should be 2n, H0L H should be 2n because H plus 0, 0 is considered as an even number. So, this should be even. Same thing here. So, this encompasses all of these. Hk is 0, H plus k is even, again the same thing and same thing. So, all the positions are general reflection conditions for all the general positions are taken care of. Now, what happens if I place atom at a special position? Placing an atom at special position, if I look at the special position, take any one of these. Let us say if I take this one here or this one, this is the same thing, any one of this we can take. So, if I take this one, then there are multiplicities only 2. So, there are only going to be 2 atoms. If I place an atom at 0 y 0, add to this the centering translation half of 0 and I will get half y plus half, half y plus half 0. So, I will get, so there are only going to be 2 terms in the structure factor, and if I plug that in, I can write the structure factor as, again I am only going to write for one atom, e to power I 2 pi, and if I just go back a bit, it is 0 y 0. So, I can write it as e to power I 2 pi k y, plus the second one would be half y plus half 0. So, e to power I 2 pi half k by 2 plus I will get y plus half. So, no sorry, the first term is h by 2, second term would be k y plus half. So, this is how this would be. If I take something common here, so I can take e to power I 2 pi k y, and what I am left with inside is 1 from the first term, and I am left with h by 2 plus k by 2. So, I will have e to power I pi h plus k. If you look at this condition and compare it with what I have here, this gives me same result as above. So, because if I place an atom in the special position, it simply says no extra conditions are there. Otherwise, in many cases, it is going to be extra conditions on top of the general conditions. One final example now I will take, which is the space group P21 over C. So, I have a 2 sub 1 along the B axis and glide plane in the AC plane. So, the screw axis is perpendicular to the glide plane. We directly come to the Wyckoff positions. So, I have 4 terms here. I have 4 terms. One can write down for all of these 4 terms the structure factor. Let me, and here are the general conditions given. I will just consider one of them. Let us consider this particular one and write the structure factor for this. So, for plane 0 0 L, so H and K indices are 0, the structure factor in the final form can be written as the scattering factor multiplied by 1 plus e to power I pi L, and I have two terms here, e to power I 2 pi Lz plus e to power I 2 pi minus Lz. This directly gives us that f is 0 if L is odd and not 0 if L is even. So, if I come back to this, basically the reflection condition is L should be an even number. Now, let us say this one, a special condition now, and write down the structure factor for this. Now, consider a special position and I will call this position as special position 2D, which basically is multiplicity is 2 and D is the Wyckoff symbol for that position that I have already indicated here. So, for this special position, I have basically two atoms, one is at half 0 half and the second atom is at half 0. When an atom is placed on a symmetry site, in this case it is on 1 bar. So, the structure factor very clearly is quite simple in this case. It is f e to power pi I h plus L plus e to power pi I h plus k. I can take out e to power pi I h common and I will get e to power inside the brackets two terms, e to power pi I L plus e to power pi I k. Let us look at this bracketed term. These could be plus or minus 1, the two terms, depending on whether L is even or odd, K is even or odd. So if L even, K odd, so one will be plus 1, other one will be minus 1, give me structure factor to be 0. So, I get extinction. Same thing if L odd, K even, I get the same structure factor again to be 0. The other is that both K and L either are odd or even, which also means, because in both cases K plus L will be even. So, if both are odd, I will have both the terms being minus 1, the structure factor is not 0. If both are even, then I get plus 1, again the structure factor is not 0. So, this gives me the reflection condition. So, if I go back to the tables, this one represents the special position 4D. It says K plus L must be even, and that is what we have got here. And this is over and above the reflection conditions given for the general position. So, with this I have completed discussion on different parts of the international table, and you will find that there are a lot of space groups where there are very large number of conditions and there are space groups that have very few conditions. So, with this I conclude the lecture here, and in the next lecture I will start the last part of this course, which is discussion on physical properties of crystals. Thank you.